All right, hi folks, this is Larry Mussolino. I'm recording a video for Module 7 homework. And let me start off with a few examples of what's called integration or antiderivatives. Now, one thing you have to remember is from the previous module, we were finding the derivative of a function. And let me give you an example. Let's say we had a function 7x to the 5, let's say, and you wanted to find the derivative. Well, when you find the derivative, you write it as f prime of x. So f prime is the derivative function. Well, there was a rule to help you with this. It was called the power rule for derivatives. And the power rule for derivatives said, if you want to take the derivative, and sometimes we use d dx to mean the derivative function, meaning taking the derivative. So if we wanted to take the derivative of x to an exponent, the way you did this is you took this exponent and actually brought it down in front as a multiplier and then subtracted 1 from the exponent. Let's do a quick example here just as a reminder of what you did last module. If I asked you, what's the derivative of x to the 5? Well, you would bring this 5 down in front as a multiplier and then subtract 1 from the exponent, so you got the answer 5x to the 4. All right, well, let's do the same thing in my example here. The only thing that's different is we have this constant 7 in front. Well, when you're taking a derivative, if you have a constant in front of x like this, you just bring that constant with you. So I'm just going to copy the 7 over. So I'm just copying the 7. And now I'm going to take the derivative of x to the 5 using this power rule, which got us 5x to the 4. And of course, I might multiply this out to give me 35x to the 4. All right, so that was the derivative function. What we want to do now in Module 7 is we want to work backwards. Work backwards. In Module 6, you were given f of x, the original function, and you wanted to find the derivative function. But now in Module 7, we're going to be given the derivative function, and you want to work backwards to find the original function. So let me give you an example here. Let's say I give you the derivative function of 35x to the 4. And I ask you, find the antiderivative. Well, antiderivative means opposite of derivative, right? The word anti means opposite. So this is asking you to find the opposite of the derivative. Well, the opposite of the derivative is going back to the original f of x, which is 7x to the 5. Okay? Now, when you find antiderivative, sometimes we call this integral. So when you see antiderivative and integral, it means the same thing. All right, well, what if I gave you, so in this example, I knew that the antiderivative of 35x to the 4 was 7x to the 5 because we started out with that function, right? We started out with the function and found its antiderivative. But what if you don't know f of x to begin with? How would you find this antiderivative? Well, there's a rule to help you do it. So let me give you the power rule for antiderivatives. Usually we're going to say this as the power rule for integration, but antiderivatives and integration mean the same thing. So I'm going to write this as the power rule for integrals, which you could think as the rule if you want to find the antiderivative. All right, here's what the rule says. And we use this symbol, it looks like a capital S. This means the antiderivative or the integral. So this symbol is called the integral symbol. It means you're going to take a derivative function and get back the original f of x. All right, well, here's the rule. It says if you're taking the integral of x to an exponent, and we use dx here, dx is a way to tell you what variable is the variable of integration. By saying dx, we're saying x is the variable of integration. Well, here's the rule. And it's going to be the opposite of the derivative rule. The derivative rule, you subtracted 1 from the exponent. Well, we're going to do it as x to the n plus 1. And then you divide by that same expression, n plus 1. And then we also put a constant out here. We write plus c as an arbitrary constant. The reason we write that plus constant there is if we were taking the derivative of any constant out here, remember that derivative is 0. So this antiderivative might be 7x to the 5 plus 13. I just made up the number 13. The reason is if I was to take the derivative of this 7x to the 5, we know that the derivative of this gets us 35x to the 4. But if I was to take the derivative of this guy over here, I would still get to be 35x to the 4. Because when I take the derivative of a constant, remember the derivative of just a constant is 0. So we're going to be putting this plus c out here as a constant. So let's do a quick example. What if I said, what's the integral of x to the 3 dx? Well, the rule says add 1 to the exponent, so that's going to make it an x to the 4, and divide by the same number that's sitting up in the exponent. Well, I have a 4 sitting up in the exponent, so I'm going to put a 4 down here, plus a constant. So this is going to be an important rule here in Module 7. Whenever you want to find the integral, which means the antiderivative, if it's x to an exponent, use this rule. All right, so with all that as background, let's go to this problem. This problem says find the integral of 4x to the 3. The dx tells me we're using x as the variable of integration. Really what this is telling you is you're given that the derivative function is 4x to the 3. Your job is to find the original function f of x. All right, well, here's the way we can do it. I can use the power rule. Well, the power rule says if you have a constant multiplying a function, you can bring that constant out in front of the integral sign. So in my example, I have this number 4 here. If 4 is multiplying x like this, I'm allowed to bring it out in front because that's just going to make it easier to work with. So now I'm going to bring the 4 out in front. And now this is the integral of x to the 3 dx. We just work that out down here using the power rule. So this is going to be the 4 comes with me. So I'm just copying that. Now I'm taking the integral of x to the 3 dx, which we said is x to the 4 over 4 plus a constant. But this 4 cancels with that 4. So we're left with just x to the 4 plus a constant. This is the final answer. Well, the good news for these kinds of problems, and by the way, remember, this is really the original function. The original function here is x to the 4 plus a constant. The good news is I could check my answer on these kinds of problems. If I wanted to check my answer, I could take the derivative of x to the 4 plus a constant. I'm taking the derivative of my answer. I should get back to this derivative function that I started with, 4x to the 3rd. Well, let me go ahead and do it. The derivative of x to the 4 is 4x to the 3rd. And the derivative of a constant is 0. So I am getting 4x to the 3rd here, which checks out. That's the function I started with. Okay, so this answer here is going to be x to the 4 plus a constant. So let me put that in here. X to the 4 plus a constant. Okay. All right. Folks, let's go do another example. By the way, please remember, folks, you have this question help that you can make use of for examples and guided solutions. All right, so let's go do another example. Let me go to, let's come here to this problem number 8. And this is similar to the example we just did. So I'm going to need this rule, the integral of x to the n dx is x to the n over n plus 1 plus a constant. Okay, you should definitely write this rule down on some kind of a summary sheet. You'll be using this rule quite a bit. All right. Now, the good news is this rule applies if the exponent n is a fraction or a decimal. It doesn't really matter. Whatever the exponent is, this rule still applies. All right, so here's what I'm going to do for my example. First thing is when you have a constant in front of x, like this 25, you are allowed to move it out in front of the integral. I'm going to do that. It just makes the integral less cluttered and just easier to work with. All right, well, now this integral exactly matches this power rule. All right, so here's what I'm going to do for this integral. First, the 25, I just copy with me. All right, I have to take that exponent 3/2 and add 1 to it. And then I have to divide by that same exponent 3/2 plus 1. And I always need to bring that constant with me as well. All right, let me work out this exponent, 3/2 plus 1. Well, the only way I can add fractions is if I have the same denominator. So I'm going to take that 1 and multiply by 2/2 just to get a common denominator. So that's going to be 3/2 plus 2/2. Now I can add fractions. You keep the denominator the same and add the numbers on top. 3 plus 2 is 5. So this is going to be worked out to be 25 x to the 5/2 divided by 5/2 plus a constant. But I can go one more step to simplify this, because whenever you divide by a fraction, if you remember, you can change to multiplication and flip this bottom fraction upside down. So I'm going to write it by taking 2/5. I just flipped and changed to a multiplication. And now I could see this 5 cancels out with 25, leaving me a 5. So finally, I have 5 times 2 is 10. So 10 x to the 5/2 plus a constant. This should be my final answer. If I wanted to, I could check my answer by taking the derivative of this red box. And if I took the derivative of the red box, I would have to get back to this starting expression here. All right, so let me enter this into the answer box here. So 10x to the 5/2 plus a constant. All right, folks, let me go back. Oh, by the way, folks, I should mention to you that sometimes you might see an example like the integral of 10 times the square root of x dx. Well, if you wanted to work this example out, all you would have to do is remember that when you see the square root of x, it's the same as x to the 1/2. So anytime you take the square root of a quantity, it's the same as x to the 1/2. For example, the square root of 25 can be rewritten as 25 to the 1/2. Okay, if you work this out on your calculator, the square root of 25 is 5. If you work 25 to the 1/2 out on your calculator, you get the same answer, 5. So the way I would work this out is write this as the integral of 10x to the 1/2 dx. The 10 I could bring out in front. And now this example is very similar to the example we did a minute ago. All right, so if you see a square root as part of the integral, always change the square root of x to be x to the 1/2. Then you can apply the power rule to that. All right, let me go back maybe because I skipped over. Let me go back to number 3. All right. So number 3 says, find an antiderivative of this function. Well, antiderivative really means find the integral. Remember, integral and antiderivative mean the same thing. All right, so they're giving me this function. And really, they're asking me to work out the integral of 6t to the third plus 14. And I'm going to put a dt out here. The dt will remind me that here we're using t as the variable, not x. Of course, it doesn't matter. We can use t, we can use x, we can use any letter we want. All right, now, there's a property that says when you're taking the integral of a sum like this, notice here's a 6t to the third and a 14, you can really think of this as taking the integral separately of each expression being added together. All right, so I'm going to do that. Let me take this integral of 6t to the third. The 6 is a constant multiplying, so I can just bring that with me. The 6 just comes with me. The integral of t to the third is t to the fourth over 4. I'm using the power rule for integration. I'll remind you. The power rule for integration says if you're taking the integral of x to the n, it's x to the n plus 1 over n plus 1. But of course, I could write this with t as the variable. So I got to write as t to the n dt. It would be t to the n plus 1 over n plus 1. So when we just took the integral of t to the third, that was t to the 3 plus 1 over 3 plus 1. That's how I got the t to the 4 over 4. All right, now I need to take the integral of just a constant out here. Well, it turns out there's a rule that says if you take the integral of just a constant, dx, it's equal to the constant times x. So if I take the integral of 14 dt, that is going to get me just 14t. So I'm going to put a 14t here. Okay. And of course, I'll put a plus c here as a constant. Well, I could do one little simplifying here because I have 6 over 4. That fraction simplifies to be 3 halves t to the 4 plus 14t plus c. This is a multiple choice question. Well, I could see right here is the only answer that makes sense. And you might say, why don't they have the c there? Well, they said, what's a possible antiderivative? So what if c was 0? Right? If c was equal to 0, then this antiderivative would be 3 halves t to the 4th plus 14t. So when they say possible antiderivative, they mean, c could be any, take on any value. Okay, so this problem was asking you to find an integral, an antiderivative. And when you have expressions being added together, you could take the integral separately of each expression. All right. Let me do a few more examples here. Let's take a look at this one. So again, this one says find the antiderivative. So really, they're asking me to find the integral. All right, so I'm going to write this as the integral of 8 times the square root of x plus 9 dx, because x is the variable we're integrating here. Well, remember, when you see the square root of x, you should replace it with x to the 1/2 to make it easy to use the power rule. So I'm going to do that. I'm going to replace square root of x with x to the 1/2. Now I'm going to take the derivative separately. Let me take the derivative here. Excuse me, the integral. I'm going to take the integral separately of each expression. Let me take the integral of 8 times x to the 1/2. Well, when there's an 8 in front of x like that, you just copy the 8 down, bring it with you. All right, now I'm going to add 1 to the exponent and divide by that same exponent. That's the power rule. Now I'm going to take the integral of 9. Well, remember, the integral of any constant is just that constant times x. So this is going to be 9x here, plus a constant. All right, but let me clean up this exponent. 1/2 plus 1 is the same as 1/2 plus 2 over 2. Well, that's 3 over 2. So this is going to be 8 x to the 3/2 over 3/2 plus 9x plus c. But whenever you divide by a fraction, you flip the fraction upside down and change to a multiply. So I just flipped 3/2 upside down. That's how I got 2/3. And here's what I'm ending up with. This would be 16/3 x to the 3/2 plus 9x plus c. And again, they said a possible antiderivative here. So let's assume c is 0. So I'm looking for 16/3 x to the 3/2 plus 9x. It looks like it's this answer B here. All right, so this problem asked you to change the square root of x to x to the 1/2. All right, folks, let me go back to, let's do an example. Let's do this one. All right, it says determine the value of a that would make capital F of x an antiderivative. Okay, well, remember, f of x here is the original function. They've given that to me as 60x to the 5. They're telling me f of x is an antiderivative. So what they're asking me to do then is to find, I'm going to erase this for a second, folks. Here, hold on a second. Let me just erase this. Oh, bear with me 1 second. All right, folks, let me, maybe I'll do this. Let me write this out. Sometimes this is a little confusing. I think this lowercase f and uppercase f. So they're giving me lowercase f of x, and then they're giving me capital F of x. Okay. So one way to think about this is if I take the derivative of capital F of x, it's going to get me back to lowercase f of x. If I take the antiderivative of f of x, I get to capital F of x. So I can really think of this as 2 ways. If I take the derivative of f of x, let's do it 2 ways. I'm going to take the derivative of capital F of x. That should get me back to lowercase f of x. All right, so that means I want to take the derivative of ax to the 6. And I know that has to get me the original f of x, which was 60x to the 5. Well, when I take the derivative of ax to the 6, this is the power rule for derivatives. The 6 comes down in front as a multiplier, and I subtract 1 from the exponent. Well, now I can pretty much see what to do with a. Because notice this x to the 5 is the same on both sides, so I can get rid of that. So what I'm seeing is that 6a has to equal 60. Well, for that to happen, a must equal 10. So by taking the derivative of this capital F of x, it's got to equal the lowercase f of x. So that means a must equal 10. So that is the answer they're looking for here. All right, folks, how about if we do a few more examples? Let me go to an example that's a little more challenging for integration. So let me go to let me come. Let's do. Hang on a second. Let me see. These two are the same. All right. Let's do an example here. Let's do number 12. All right. So I could see here they're asking me to integrate x to the 6 plus 1 to the exponent 6 times 6x to the 5 and a dx. All right, now I know if I had the integral of x to an exponent, I could use the power rule. All right, but my example isn't just x to an exponent. There's this parenthesis being raised to the exponent 6. I don't have just x to an exponent. I have a parenthesis being raised to an exponent. When you see this kind of a setup, we need to use a method. It's called a substitution method. So we need a substitution method. And sometimes this is called U substitution. All right, here's what it says. Step 1, let U equal the expression being raised to an exponent. All right. Well, in my example, I could see that's this contents of this parenthesis. So I'm going to let U equal x to the 6 plus 1. All right, let me go to step 2. Step 2 says take the derivative of this U expression. And you might say, well, why are we taking the derivative? This is an integral problem. Well, for this method, we need the derivative. I'll show you why in just a second. So step 2 is take the derivative of this U expression. Well, this is going to be the derivative of x to the 6 plus 1. Well, that turns out to be, I'm going to write it this way. Let me write it as du dx. So I'm going to take the derivative du dx, and I'm taking the derivative of x to the 6, that's 6x to the 5. And of course, when I take the derivative of 1, it's just a 0. So I'm going to take du dx and get 6x to the 5. All right, let me go to step 3. Step 3 says solve the equation from step 2 for dx. What that means is I want to get dx by itself on one side of the equation. Let me show you what I mean. I'm going to go back and write du dx equals 6x to the 5, right? That was what we got from step 2. Algebraically, I want to get this dx all by itself on one side of the equation. Well, the first thing I'm going to do is I'm going to multiply both sides by dx to cancel out the fraction here. So that dx cancels out with that dx. So now I have du is 6x to the 5 times dx. But remember, we want to get dx by itself. So now I'm going to divide both sides by 6x to the 5. All right, finally, I have dx equals du over 6x to the 5. All right, let's go to step 4. Step 4 is replace u and replace dx. And your goal is to get an integral that looks like u to the n du. Because if you can get an integral that looks like u to the n du, this is the power rule. This would be u to the n plus 1 over n plus 1 plus a constant. All right, so I'm going to do that. I'm going to go back to our original integral. Here it is. And I'm going to replace this quantity in the parentheses with u, because that's our original definition of u. So this is going to be u to the 6. This 6x to the 5, I'm just going to copy it down for now. It's going to cancel out in a second. Now, here's where I substitute in for dx. Remember, dx was du over 6x to the 5. So in place of dx, I'm going to put du over 6x to the 5. Okay, let me write this down here just to get it out of the way. So we said in this here, we said u was x to the 6 plus 1. All right, well, notice the 6x to the 5 on top cancels out with that 6x to the 5 on the bottom. I'm left with just an integral that has u in it. So I'm left with the integral of u to the 6 du. Well, this is a nice integral that exactly matches the power rule. I'm going to add 1 to the exponent and divide by that same exponent. But the last step is I don't want to leave my answer in terms of u. I want to leave my answer in terms of x. So now the last thing I'm going to do is replace u with its original definition, which was x to the 6 plus 1. So I'm going to write this as x to the 6 plus 1 to the 7 over 7 plus a constant. Here is the final answer. All right, folks, so this is a little bit of a complicated process because we had to try to make the integral they gave us look like the integral of u to the n du. To do that, you can use a method it's called u substitution. You let u be the expression being raised to an exponent. In our example, u was x to the 6 plus 1. Then you take the derivative of u with respect to x. We got 6x to the 5. We did that. Then do a little bit of algebra to get dx by itself, because when you go back to the integral, you want to replace dx with this quantity du over 6x to the 5. When we did that, we ended up with this integral, which is u to the 6 du. That exactly matched the power rule. So our answer here is x to the 6 plus 1, whoops, to the exponent 7 all over 7, whoops, to the exponent 7 all over 7 plus a constant. All right. Folks, let me do one or two more examples here. You might be wondering, what is the purpose of this integration? Why are we working through this integration? And the answer is integration has the geometric equivalent of finding the area under a curve. Let me go back to the previous example. Let me go back to a previous example here. All right, well, here's what they're asking me to do here. They say find the area under the curve y equals 7x squared that is between the lines x equal 1 and x equal 4. Let me draw a little graph of this to get an idea. What are they talking about? Well, let me draw the function 7x squared. That's going to look something like this. So this is y equals 7x squared. I'm going to draw the vertical line x equal 1. Maybe it's here. And I'm also going to draw the vertical line x equal 4. Maybe that's there. So here's the vertical line x equal 1. Here's the vertical line x equal 4. They're asking me to find this green area under the curve. Well, it turns out we can use integration to find this exact area. So if I want to find this green area, here's the way I do it. I write the area is the integral of the function they gave me, which is 7x squared dx. But then I've also got to specify what is the lower bound and what is the upper bound. Really, what is like the left side of the bound for the area and what is the right side for the bound of the area? Well, in our example, the lower bound is 1, the upper bound is 4. We write this on the bottom and top of this integration symbol. All right, when you do it this way, this is called a definite integral. So when you have this lower and upper bound, in our example, put a lower bound of 1 and upper bound of 4, we call this a definite integral. All right, so here's the way you do this. First, I'm going to integrate 7x squared. Well, I keep the 7. Now I'm going to integrate x squared. That's x to the 3rd over 3. But I still have to evaluate it from this lower bound of 1 and an upper bound of 4. To show that, you put a vertical line here. You put a 1 on the bottom and a 4 on the top. What that's telling you is you still have to evaluate this integral function between these two limits of 1 and 4. Okay. And when we do this, we're going to come up with a number as an answer, because that number is going to be this area that we're looking for. All right, so here's how you do it. What you do is you plug in the upper bound into this function. So our upper bound was x equal 4. So I'm going to plug x equal 4 into this expression. If I do that, that's going to be 7 times x to the 4 over 3. Then what you do is you subtract when you plug in the lower bound. So now I'm going to plug in the lower bound of x equal 1. And this subtraction is required, and that is how you evaluate a definite integral. Well, if I plug in the lower bound, that's going to be 7. Oops, I'm sorry, I should have put a 4 here. I made a mistake here. Let me back up. I should have been putting a 4 in for x here. So this should have been 4 to the exponent 3. And I'm going to do the same thing back here. I'm going to plug in a 1 in place of x. That's going to be 1 to the third over 3. All right, so let me say this again. Here are the steps we followed. First, we worked out this integral using the power rule. Then you plug in the upper bound into this expression. That's what we have here. Then you plug in the lower bound to this expression. That's what we have here. And you subtract these two numbers. All right, let's work it out then. All right, let's see. 4 to the exponent 3 is 4 times 4 is 16 times 4 is 64. So that's going to be 7 times 64 over 3. And 1 to the third is just 1. So that's going to be 7 times 1 over 3. Well, 7 times 64 on my calculator, this is 448 over 3 minus 7 over 3. I'll just subtract these fractions. You keep the common denominator, subtract the numbers on top, 441. So I think my answer is 441 over 3. If I divide this, I get 147. So this area, this green area we just found, is 147 square units. Could be square feet, square inches, whatever I'm measuring. So this answer here was 147. All right, folks, so this is called a definite integral. It means you're evaluating an integral from a lower to an upper bound. All right, folks, let's do an example where you're actually given a graph. All right, so let's come to this one. Well, in this example, there's kind of two ways I could do this. They're asking me to find the area under this curve from a lower bound of 2 to an upper bound of 4. But because this curve is so simple, you know, y equals 2x is the graph of a straight line, I can actually do this using geometry. I don't need integration here. But let's do it both ways. Let me do it the integration way. The area would be the integral from the lower bound 2 to the upper bound 4 of the function 2x dx. All right, why don't we work this out? Well, if I take the integral of 2x, the 2 comes with me. When I take the integral of x, remember this is really x to the 1. I add 1 to the exponent, that would make x to the 2 over 2. And I'm going to evaluate this from a lower bound of 2 to upper bound of 4. But this 2 cancels out with that 2. So this is just going to be x squared from 2 to 4. And remember, what you do is you plug in the upper bound. Here I'm going to plug in x equal 4. And then you subtract. When you plug in the lower bound here, it's x equal 2. So I'm going to plug in x equal 4. That's going to be 4 squared. Then I'm going to plug in the lower bound 2. That's going to be 2 squared. So this is going to be 16 minus 4. It looks like this is 12. So the area is 12. But I could do this using geometry. Maybe I can make this graph a little bigger. All right, let me come here to this graph and let's use geometry, because what I could do here for this graph is I could break this up into 2 pieces. Let me break this up into graph A, region A and region B. Region A is a rectangle. Well, I know the area of a rectangle is length times width. So the length is 2. I'm sorry, the width is 2 and the length is 4. So the area of that rectangle is just 2 times 4. That's 8. Shape B is a triangle. The area of a triangle is 1/2 base times height. The 1/2 base times height. The base is 2, and the height is also 4. So this is 1/2 times 2 times 4. That is 4. I'm going to add these two areas together. 8 plus 4 is 12. I get the same answer, 12. So I could either do this using just simple geometry, or of course I could use this definite integral approach. Either way, I'll get the same answer. All right, folks, hope this is helpful as you're working in this Module 7 homework. Please remember to use videos that are in my math lab. There's also videos posted in Canvas, by the way, folks. Let me show that to you. Maybe you have not tried this, but oh, before I leave here, remember question help. Here's a video. Here's a view and example. Here's a help me solve this. Let me go into Canvas for a second, because I just want to show you that when you go into the module, so let me come here to modules, and I'm come here to module 7, and I'm coming here reading and resources. So notice here's the reading for module 7, right? It's sections 25.1, 25.2, and 25.3. But if I click up here in this tab called videos, here are 3 videos covering topics that we just talked about. So please check out these videos as well. All right, folks, let me know if you have any questions along the way, and hope this is helpful as you're working in the Module 7 homework.